All right, thank you everyone for coming to the Graphs and Matroids seminar for the first talk in the new year. Today's speaker is Stephan Kreutzer, who will be talking about tangles for directed graphs.
Well, thanks very much, and thanks very much for inviting me to the seminar. When I got the invitation, I was a bit, well, puzzled because it's the Matroid seminar, and my knowledge about Matroids is, well, let's say, not excessive, so to speak. So I was wondering what I could talk about that would come close to Matroids, and this is the closest I could find. And it's close to Matroids because I spent about half a year trying to prove something in the paper using Matroids and failed. And when I gave up on the Matroids, then the proof was actually very easy. So that was my this as close to Matroids as got. But it's probably not a problem of Matroids, but more of the user who was trying to sort of fool around with things he doesn't really understand. Anyway, so let's get started. So this is on directed tangles, and it's a joint work with Ahontia Giannanopoulou, Ken Ichikawa-Bayashi, and Ojong Kwon. And yeah, all of it, more or less. All right. So as a bit of introduction, so what tangles are is just a way of formalizing highly connected regions or pieces in the graph. Yeah? And clearly, if you have a graph, yeah, like this one here, and then one of the fundamental problems we might be interested in is to sort of identify those pieces of the graph which are highly connected. Yeah. And here it's easily seen what are the highly connected pieces. Yeah, so we would consider each of these things fairly highly connected because it's a bit grid. But in here we see if you were to cut the graph in pieces, you would probably attack somewhere here. Yeah, and so one question is how can we actually formalize and identify highly connected pieces of the graph? And then of course we would also like to decompose the graph into its highly connected subgraphs, or components or regions. Or sorry, there's an annoying animal on my iPad. So it's gone. Just kidding. Right, and of course, one way of pursuing this is the usual route. So if you start with the graph, it's an undirected graph for now in the first few slides. And then you look at its components, the connected components. So then you're one connected, and then you cut vertices, and you get a block graph, the blocks being two connected. And then you can pursue further and cut along two separations, and you get Tutt's decomposition theorem. So you cut along the two separations to get a tree decomposition into pieces of the graph which are either three connected or cycles. And then you take your three connected components and then you cut along three separations, and then it doesn't work anymore, really. Yeah, and then you skip the three and you cut along four separations, and things still don't work. And so it's not so clear what to do here for connectivity. And the problem is somehow how can we then formalize highly connected components in the graph? Yeah, so if you can't find them by just cutting along k separations to get k plus one connected components, then we need something else. And that's what tangles are. Now, the reason we looked at directed tangles then later on wasn't so much following this route of block graphs and decomposing into three connected components and so on. It was more motivated by the structure theorem for undirected graphs. So the question, what is the structure of a graph if you know that it doesn't contain a large click minor? And so that's of course the structure theorem, Robertson and Seamus structure theorem for large graphs with no large click minor. Let's say we have a graph and we know it doesn't have a large click minor. We would like to understand what the structure of this graph, what we can learn about the structure of this graph, or reasons why it doesn't contain the large click. And obvious reasons could be because the graph is planar and then it shouldn't contain two big click minors, or more generally, it might be embeddable into a low genus surface. Yeah? That's not sort of the genus not being high enough to encompass the big click minor. Yeah, and now you could ask to describe your graph in terms of these embeddability into low genus surfaces. But one observation, of course, is if you look at a graph like this and we want to find a large click miner in it. I mean, here, of course, you wouldn't find any, but if you had a few more edges somewhere, yeah, in between these things, then possibly you would find one. And clearly, if you're looking for a large click miner, then the majority of this click will sit in one of these components. Yeah? So you could have whatever, maybe a large click miner here, and then maybe it's using a little bit some path along here and so on. But the majority, I mean, the biggest part of the miner would sit in a highly connected region, yeah, obviously, because a large click you can't sort of squeeze through such a tiny loophole. Yeah? And so for that reason, you could think, well, maybe if that's the case, that click miners would essentially be captured by one of these things, then one could ask, maybe we can explain the structure of highly, well, if you can explain why a highly connected region doesn't have a large click miner, then maybe this can be generalized to the structure of the entire graph. And again, what you would need here is a way of formalizing what a highly connected region actually is in the graph. Yeah. And so much for, well, maybe motivation. And now this leads to the definition of a tangle, yeah, where we use this idea that if something is highly connected, then if you look at low order separations, then the majority or the bigger part of this highly connected piece would sit on one side or the other of any separation. Yeah? So if in general we have a graph that would sit like this, yeah, and you have a separation AB. Separation, of course, being just a pair of subgraphs, yeah, that together are the entire graph. And then our highly connected region, let's say we want to find this one here, the bigger part of it would sit on one side or the other, but it can't just be evenly split along the two sides. And so that's basically the idea, yeah. And so the general idea, of course, of identifying the highly connected pieces by just cutting along small separations doesn't really work so well, as we can see on the grid. Yeah, because the grid here being fairly well connected, yeah. So if you want to really disconnect it, you need to chop off quite a bit, yeah. So just cut through it. But of course, for every single vertex, we have a separation of order 4 that would split it off. Yeah? Or let's more generally, if you have low order separation, then it could sort of split off a piece of the grid. And so there isn't really any vertex in the grid that you could say as being the representative of the grid, yeah, of this connectivity of this region here that we want to identify. Because every single vertex in our highly connected region will be split off by some separation. Yeah, and so the question would be, what kind of separations would we take to identify, let's say, this highly connected region? Yeah. And the answer that's taken by tangles is, if you don't know which one to take, then let's take them all. And so the general idea just being, well, if you take, let's say, this order 2 separation here, yeah, so with these two sides, A and B, then we can just ask the separation on which of your two sides is the highly connected piece that we want to define. Let's say this is the piece we want to, let's call it R for now. Yeah, and then the separation would say, well, it's here. Yeah. And then we could find ask the next separation. Let's say, poor choice of colors here on one side. Let's say this one here, and it would also say the region R sits on this side, and so on and so forth. So we could just ask every order 2 separation, and each of them would tell us on which side the majority of our region would sit. And this would also be true for these tiny things. Well, order 2 here may not be enough, but maybe just if you ask a little separation like this, it would also tell us the majority of our grid sits on this side. Yeah. And so consistently, if you take them all and ask every low order separation which side is the grid, then this would give you an information. This would more or less define actually your the region you would like to look at. Yeah. And so a tangle is really just that. It's a consistent orientation of all low order separations that would point towards one specific piece of the graph. Yeah. And consistent meaning, obviously, what you cannot have is that you ask this separation here, and then suddenly it's telling you no, it's sitting here, right? Whereas the next one would just say here it's sitting on this side. That would not be consistent, and it wouldn't point to anything interesting. And this is the idea of undirected tangles, and then obviously also of directed tangles that come later. And so here's the definition by Robson and Siemer in graph -10, where a tangle of order k is just a set T of separations in the graph G of order less than k. So, and we have three conditions here, so that if any separation AB of the graph of order less than k, we take one of the two orientations into the tangle. So for the separation AB, either this orientation AB or the orientation BA is in the tangle. And if we have three separations in T, so A1, B1, A2, B2, A3, and B3, then the union of the left side, so A1, A2, and A3 together should not be the entire graph. Yeah. And here, by the way, separations are subgraphs. Yeah, so the union here really is the union of subgraph. And the last condition is that if you have any pair AB, any separation AB in our tangle, then we don't want that A contains all vertices. Yeah. You think this follows from the second condition, but it doesn't really, because these are subgraphs, and so it could be that that A has all vertices, and there's just a single edge that sits on the B side, yeah, of it. And so we have this extra condition here. Yeah, and this orientation here is just what I just mentioned. So the separation pointing towards the highly connected region, and for that reason we call the B side, if AB is in a tangle, then B is the big side, because it contains a bigger part of the region we want to define, and A is the small side. Oh, and that's a tangle. And so if we were to do this here in this graph, then you would find sort of more or less 4 tangles of sufficient order, 5 actually, 6 counting is not my strength apparently here, which you could sort of consistently orient to each of these 6 subgraphs. Yeah. Okay, now that we have tangles, yeah, then of course the next question is then, can we actually decompose the graph into its tangles? Yeah? And so here a bit of notation that I'll use later quite a bit. So if we have 2 tangles, T and T prime, then a separation AB is said to distinguish the 2 tangles if one orientation, let's say AB, is in T but not in T prime, whereas the opposite orientation is in T prime but not in T. Yeah, so there's a separation, and the T sits on one side and T prime sits on the other side. Yeah. And then this notation here, kappa of T and T prime. This is just the minimum order of any separation that would distinguish between T and T prime. Yeah. Of course, there could be many separations distinguishing the 2 tangles, and we take the minimum, the minimum order of any such distinguisher. And then the theorem that's proved in graph -10 is the following: if T is any set of distinct tangles, yeah, so which are distinguishable pairwise, then there exists a tree decomposition. Yeah, so this is just a standard tree decomposition of the graph G of edge width less than k, with the following property. So the vertices of our tree are just the tangles in T. And if we have an edge in the tree decomposition, then maybe let me just draw a picture that's perhaps easier. So we have a tree decomposition of our graph. Yeah. And if you have an edge, let's say this one here, then the nodes of the tree decomposition correspond to our tangle. So we have a tangle maybe here and a tangle T prime here. And then this edge defines the separation of the graph. Yeah? So we take the union of all the backs on the left-hand side and all the backs on the right-hand side. And then the requirement is that if T is here on the left, let's call this A and B, yeah? Then we have BA is in T, whereas the tangles on the other side, they would have AB in T prime. Yeah? So as usual, of course, every edge of the tree decomposition defines as a separation, and this separation would distinguish between every tangle on the left from every tangle on the right. And then we have an extra condition, namely well, distinguish, of course, you can a lot. But what we're also interested in is looking at if you have two tangles, T and T prime, we would like to look at the minimum order distinguishers, so the minimum order separations that would distinguish between the two tangles. And then the third condition just says, if you look at the path in the tree decomposition from the node that corresponds to tangle T to the node that corresponds to T prime, then the edges on this path that define separations of minimum order, then this would also be the minimum order of any separation that would distinguish T from T prime. Yeah? So we could have here E prime, of course, would define another separation, but maybe this is not of higher order than the order of E. Yeah, and then if E is the minimum order separation, it would be a minimum order distinguisher between these two tangles. Yeah, so this tree here also is sufficient in the sense that it captures the best way of separating these tangles. All right, so much for so here's a nicer drawing of the same picture. Yeah. So these are the properties that we can prove, or can be proved for the undirected case. And yeah, so now, of course, we want to do the same thing for directed graphs. Yeah. And a side remark, yeah, which we hoped for a while that we could use. So these are tangles for just undirected graphs, but then Diestel and his group, the various members of his group are fairly long series of papers. They managed to vastly generalize this idea of tangles for undirected graphs and redefine this in a very, very abstract setting, abstract separation systems, and got the same results. So tree duality between tangles and tree decompositions in this sense. And this allows them to apply the theory of tangles in almost everywhere, really, yeah? in a broad range of applications, from sociology to whatever you ask. Yeah? So basically everything that exists, you could throw this theory of tangles on it, except for directed graphs. Yeah? And I've been trying to get Reinhard Diestel to get this to work for directed graphs for quite a while and never really caught up. And it seems it doesn't really work. It's just at least the most generalized, the latest versions of these papers, they're super abstract, and yet something doesn't work for directed graphs. And so we can't take the we really have to prove everything by hand for the diagraph setting. And I don't really know why, but maybe there's an even more general theory that will capture everything, but it doesn't exist yet. So maybe just a very quick remark, why actually did we look at directed tangles? So like I said, the motivation came from the structure theorem for undirected graphs, where tangles play a role. Yeah. If you want to describe the structure then of graphs with excluded minus, then the tangle decomposition theorem gives us the global structure because it decomposes the graph into its highly connected pieces. And then the rest in the theory, you would start looking at each tangle and describe the structure relative to a tangle. And then you would apply the grid theorem to get large grids. And then you would have a flat wall so that things become flat. And then you start, and then you have to work actually from that point onwards. So that's where the real work then starts. And so some time ago, Ken and I, we thought we could try to generalize, well, or to adopt or modify, or however you want to translate this to from undirected graphs to directed graphs. There was a notion of directed tree width, which was introduced by Johnson, Robertson, Seamer, Thomas, and also Bruce Reed in the 90s. And so there was this concept of directed tree width, and there was also the appropriate notion of grids that would correspond to directed tree width. At least it was conjectured at the time. And so we thought, well, we could have a go and prove a directed excluded grid theorem, which we did eventually. And from that, then we get this flat wall, directed flat wall theorem. So of the buzzwords I mentioned on the previous slides, we have them now, except for the Tangle thing. And so the obvious next question was, can we actually adopt the Tangle decomposition lemma to directed graphs? Yeah, and we think, some variant at least. And this is what I want to speak about next. Yeah. And the idea would be just really to have the obvious translation to directed graphs working. As always on directed graphs, it doesn't work so well, but it works somewhat. Yeah, and you'll see what I mean by this in a few slides. Okay. So directed separations and tangles, and directed separations, just to fix some notation, of course. So in a digraph, we have the same concept. So we have a nice directed graph, yeah, and then we want to separate it into two pieces. So this A and B, and then these would be the separated words in the separator. But because it's a directed graph, you will have edges crossing from one side to the other. So that's at least we shouldn't forbid this. And we allow in the directed separation that you can have edges like this, or you could also have edges the other way around, but not both. Yeah. Otherwise, it wouldn't be really a separation. So if you allow edges from A to B, then these edges would be forbidden. Yeah. And for that reason, because you do have edges that are neither part of A nor part of B, because they cross from A minus B to B minus A. For directed graphs, whether you take separations as pairs of subgraphs or just sets of vertices doesn't really make such a difference, because you would never, the union of A and B will not be G anyway. But to be consistent, I define a directed separation still to be a pair of subgraphs, yeah, allowing these cross edges. And so this gives the notion of separation, and then a tangle is just defined in the obvious way. If you have a directed graph, and then a tangle is just a set of separations of order less than k, so a tangle of order k. If you have two properties, one is for every separation AB of G of order less than k, one of the two orientations would be in your tangle. And the second condition would just be if you have three separations in T, so A1, B1, A2, B2, and A3, B3, then you don't want that all vertices of G are contained in the union of the three small sides. So A being the small side again, and B being the big side. So the union of three small sides should not contain every vertex. And because we require three small sides not to span all vertices, then of course we don't need the third tangle condition explicitly. Okay, that's a tangle, yeah, and so here let's have a quick example that we pop up time and again in the next few slides. Yeah, so what I mean by this drawing here is each of these things here is supposed to be some maybe large clique or something, yeah, something big, yeah, that would define a tangle, and then they're connected like this. And then, for instance, if you look at B, we want to define this as a tangle. We could look at all order 2 separations that would separate B from the other cliques. And here is something strange here, because one separation would be we take the vertex 2 and 3 as separator, and then we get this separation here. And this would actually distinguish, well, these two sides from the other three. Yeah. And you'll see later why I mentioned exactly this, yeah, because this is actually also the minimum order separation that would split B from the rest. Yeah. And if you want to define D here, then we could just look at these separations, and everything that points towards this side here would be the big side, and then identify the tangle E. Yeah. Okay, so I'm not sure if my explanation made so much sense. I guess the example itself was fairly obvious before I started to explain it. Yeah, okay. Okay, that's a tangle. And now, of course, we would like to have the same thing as for undirected graph. So here, for those with good eyes or big monitors, it's the theorem for the undirected case. So we wanted to prove a similar thing. We wanted again that if you have a set of tangles which are pairwise distinguishable, let's say of order k, then we want a directed tree decomposition of G of edge width, whatever this is, with the same property. So the vertex set of the tree decomposition should be the set of tangles. Then if we have an edge in the tree decomposition, then we want that it's distinguishing all tangles from the left from all tangles from the right. And again, edges of minimal width should be minimum order distinguishes between the tangles. Yeah, so that would have been the idea. That we want such a thing. The problem is it's actually not true, I think. And I give some reasons why it doesn't work. Yeah. So the problem seems to be, I say seems to be because it's not yet a formal. I mean, of course, you could define it in any way. So just to say that such a thing doesn't exist is hard to prove. Yeah? But what happens is you can't have condition 2 and 3 at the same time. Yeah? So just to go back, what the conditions are saying is if you take any edge, yeah, and you look at the separation that it defines, then you want that this separation separates every tangle on this side from every tangle on this side. This would be condition 2. And at the same time, you want that if E is a minimum, is the lowest, has a minimum order of any separation on the path between two tangles, then it should be a minimum order separation between, let's say, T2 and T6. And both at the same time seem hard to exist. It doesn't really exist, I think. And I'll give you an example of what's for the problem in a few minutes. So we prove something, and this is for what we call tree labelings, and I'll define that formally in a moment. Of course, what the more general, the more natural thing you would like us to prove, I guess, is that we prove that there's a directed tree decomposition of the digraph G, which distinguishes all maximal tangles or all tangles in T. And I do not expect you to know what the directed tree decomposition is, and I'm also not sure I want to define it, maybe if there's time later on. But here we can prove even less because here we only managed to prove an approximate version. Yeah? So we need to blow up the order of the separations a little bit. Yeah? But this is simply because things are a bit weird in the digraph setting. And what's weird, I'll explain in a few slides. Okay, so let's first prove the nicest thing. And so that's the tree labelings, yeah, and it's defined like this. So this is the definition, and I give you the example. So we fix now a digraph for now on everything is directed, and we have a set of tangles which should be pairwise distinguishable. Otherwise, of course, you can't have a decomposition. And then a tree labeling for this set T of tangles is just a triple consisting of a tree. Yeah, it's a rooted tree. Or a directed tree, you can take, the direction here doesn't matter, so we can just take a rooted undirected tree. And we have two functions. The function beta here maps every vertex of the tree to a tangle in T. And then we have gamma, which is the guarding function, and this maps every edge of the tree to this set here, and this set is just the set of all separations in the digraph. Okay. So every edge is just labeled by a separation. And then we want the following properties here, namely again that this beta is just a projection between the vertex set of L and T. We could just have said that L has T as vertex set, it would have been the same thing. And we have two conditions here. One is that if we have two different tangles, T and T prime in L, and we look at the path between them, then we have this minimum order property. So every edge on this path, so that the separation gamma of E, yeah, we call it, this is here mapping edges to separations. If the separation gamma of E has minimum order among all separations along this path, then the separation must be a minimum order distinguisher between the tangles T and T prime. Yeah. And the other third property is if you have any edge in the graph, in the tree, yeah, let's say S and S prime, then there must be tangles T and T prime on opposite sides of the edge. Yeah. So here we have the edge E, and this would be S and S prime. And then here we go on and so on. And so at least it should be the case that there's a tangle here and a tangle on this side. And gamma of E is a minimum order distinguisher between the two tangles, T and T prime. Yeah, these are the properties. And if you remember the undirected definition, then you see the difference, perhaps. In other words, let me point this out. What we do not require is that every tangle on this side is distinguished from every tangle on that side by the separation here. Yeah. So unfortunately, it could be that you have some tangle T1 here and some tangle T2 here, and they're not distinguished by this. Yeah. And this is something that seemed to be unavoidable, and I give you an example. So the next best property then that we could think of is just that at least there's no useless edge in here. So if an edge is in here, then it has some purpose of being in the tree. Namely, it's the optimal distinguisher between two tangles, one on the left and one on the right. Yeah. That's the condition. Okay, then a bit of notation. So if E is an edge in the tree, then gamma of E is a separation at E, of course. And the order of an edge is just the order of this separation. Yeah. And then we say the order of the tree labeling is the maximum order of any separation along the edges. And that would also be, if you want, as well, the edge width, you may call it this way, of the tree. Yeah, so far so good. So this is the nicer drawing version of it, just to record. These are the things that we want. We want every edge distinguishes two tangles in an optimal way, and if you have tangles along the path, then the minimum order edges would also be the best distinguisher between the two tangles. All right, now let's.
I've got a question just for my own understanding of the definition, which is how does the tree being rooted come into play?
It doesn't yet. It comes later. That's why it's in parentheses. For the tree labeling, you don't actually need the root. We need this if you want to convert this to a directed tree decomposition later on, because these are directed trees. Yeah.
Thank you.
I mean, if you were to ever look at the proof, you would see that there's a very natural direction that comes out of the proof. Yeah? So you will actually get a directed tree, and then just you can ignore the direction, as it were. But it comes automatically. All right, and the theorem I would like to then we can prove is that every set T of pairwise distinguishable tangles in the diagraph has such a tree labeling. Yeah. And if you're interested in algorithms, if let's say if you give me a number k along with this set T, then we can, with a property that the tangles in here are distinguishable by order k separation, then we can compute this tree labeling fairly efficiently. Well, for fixed k and polynomial time, yeah, and but it works also for general sets. Okay, so let me prove this, or at least give some ideas how to prove it. And so the best version, the first version we can prove is we look at a set T of tangles, each of them being of order more than L, and they have the property that any pair of tangles in T can be distinguished by a separation of order L, but not by a separation of order less than L. Yeah. So they're all pairwise sort of. So in Jim's notation, it would be kappa of T and T prime is exactly L for all T and T prime in the set T. Yeah. And in this case, actually, we get exactly the same properties as in the undirected case. Yeah, we get a tree labeling with the properties I discussed in the previous slide. But in addition, every separation labeling an edge has order L. And here we get this property that if you take any edge, let's say this one, then it's labeled by a separation gamma of E. And this one would distinguish every tangle on the left-hand side from every tangle on the right-hand side. Yeah. So this is exactly the property you would guess in the special case for undirected class as well. Okay, so let me prove this first. And before I prove this, maybe let me also explain, I guess those of you who know the undirected tangle theorem, how you prove it, just what doesn't work. I mean, what's the problem? Because then we see how to prove it. So we want such a tree here, of course. Yeah. So this thing, and these are the tangles of our set T, and we need to find sort of the edges here. Each of them needs to be labeled by some separation. Yeah, and let's say if you look at T1, then this separation here must distinguish T1 from everyone else. Yeah? And same for all the other tangles and edges here. And so what we just do is we start with the set T, and then for every tangle T from our set, we take a separation, let's call it sigma of T, which distinguishes T from the rest. Yeah, so that would be the idea. Yeah, let's say. And what happens then is you will pick a set of separations. Yeah, so this would be AB, and then some tangles will contain BA, yeah, the tangles here, and some tangles will contain AB possibly. So let's say we have T1 and T2 up here, and we have T3 and T4 up here. Yeah, and then we take a second separation that would also distinguish some tangles. And now it could be like this, let's say. Yeah. So it would separate T1, T3, and T4. Oops, that's not what I wanted. Oh, never mind. Yeah. So it separates these three tangles from this one. And now, because we want a tree, then we would normally want a laminar set of separations. Yeah, this is how you would prove the theorem in the undirected case. And if these were undirected graphs and undirected separations, we could uncross. Yeah, we could just say, okay, well then you take this corner and this corner, and that would be separations separating T2 from everyone else. In the directed setting, it doesn't work. Yeah, and I should also, I guess, explain my notation here in the drawing. Yeah. Remember that in directed separations we have cross edges, and these things here always symbolize the direction you would allow cross edges. So in the separation AB, we can have an edge that goes from vertex on top to vertex on bottom, but then if you want to go back, you would need to intersect a vertex in this separator. Yeah, and the same for the red separation here. We have again separator here, and you can have an edge that goes this way, but if you want to go back, you have to go through the separator. And because we always drew the separations in exactly this way on the blackboard, I will always call this side here A the upper side or the top side, and this would be the bottom side. Yeah. I know it doesn't really make so much sense. It would probably better be called the outgoing side and the incoming side, but yeah, as long as I draw them, I hope that's fine. Yeah, for the directed class, it doesn't work. Yeah, because these things here are no separations. Yeah, so if you wanted to take this as one side of the separation, and then this being the other side, this would not be a separation, because by this cross edges here, you can go from here, you can jump in, and then you can jump out. Yeah, and you could complete the cycle here, you would have cycles that contain a vertex on this side and also of the other three corners. Okay. And this is a bit of a problem for the proofs, and it makes just things. So this is the reason why the proof of the undirected case just doesn't go through simply. Well, what is true is if you have a pair of crossing separations like this, then two corners uncross, and namely this corner here and this corner. Okay. Because these are separations, and so if you call this the top side and this the bottom, then you could take this corner here, and then this would be one side of the separation, and the rest would be the other side. And the same here for the lower right corner. And you can prove submodularity just in a way for the undirected case. So and you see by picture here, yeah, of course, the if you're interested in the top corner, then this corner here, this corner, of course, has the same, most the same order of these two. Yeah. So either or the other corner. Yeah, so if you have order k separations, two of them, then one of them has to be of order k. And that's nice, and that's essentially the property that gets the proof through in the end. Now, if you're in the particular nice situation that we now have a set of tangles, yeah, and we know that every pair of them, distinct pair, of course, is distinguishable by an order L separation, but not less. Yeah. Distinguishable. Then you get the following. If you now have a pair of crossing separations with a property that they distinguish a tangle here and also a tangle on this side, then you can uncross, and because this corner here would separate T from T prime, but also this corner here would do the same thing. It would mean both corners have to be of order exactly L, right? It can't be that this thing here has only L minus 1 vertices, because then it would separate T from T prime with only L minus 1 separation, which is not allowed. Yeah, so we don't have this. And this is a nice thing that will be helpful just in the proof. Okay, so I hope this made a bit of sense, just to explain what's different from the undirected setting, why we can't just adopt the same proof. And so the first lemma that we can prove is if you have such a crossing pair of separations. Yeah, so what the lemma says is we have separation AB, and this separates some tangles, let's say T1 and T2 from T3 and T4. Then if you can guarantee that you also have a separation, yeah, here CD, which would separate tangles here like this, then we can shrink one side. Yeah, so if they're like this, let's say, then we can take this corner here, and that would have strictly less tangles on this side and distinguish all tangles here from all the tangles in these three corners. Okay. This is what the lemma says. And what it allows us to do is simply, if we take sets of separations distinguishing tangles from T, then we can always shrink one side. And so eventually there must be, for every set T that we're given, there will be a separation that has only one tangle from T on one side and everyone else sits on the other side. Yeah. Yeah, so this is exactly what this lemma here is saying. And this may not be true for all tangles. Yeah, so some of them you can't separate from everyone else, but at least one of them you can separate from all the other tangles in T. And then this is essentially what the proof is doing. So let's say this is our set T, yeah, and it will be TA up to TE. And we're looking at separations of order 2. Right? And so, which distinguish tangles in T. And I don't want to go into the formal setting, but of course, let's say we start from E and we want to take a separation that separates E from everyone else. And we want to make the site containing E as small as possible. So we would perhaps take this separation here, these two vertices as a separator. And then we see it has E on one side and everything else on the other side. And the same we could do here for D, let's say. Yeah, here we could just take these two vertices, and then we have this separation here. It separates D from all the other tangles. And this is outgoing, as it were, because we are sending edges out, as you see here, these edges here. But all the incoming edges end in one of these two vertices. Yeah, but now if you look at B, then this is not, well, it's not possible. Right? Yeah, because we want these 6 vertices, well, the click B here, right? And what we can do is just take this. We take we take the outgoing vertices. So we would take, no, this one, this vertex and this vertex here. And then we get these. And what we see is it's not just containing B, but also the other tangle D on the bottom. But every incoming edge ends either in 3 or it ends in 2. Right? And then we're sending some edges out. And the last example would be C, which is symmetric. We take this one here and this one. And we get this separation. Yeah. This is even more generous because we have 3 tangles on one side of separation and then the rest is here. And then the last one would be A, but A can be split off easily from the rest. So, just like this. And so what we see is different types of tangles in here, because there are some which you can just separate from everyone else. And then some where you can't separate them by minimum order distinguishes from everyone else. And so we call them, we assign ranks to them. And so this would be a tangle of rank 1, yeah, because you can separate it from everyone else. This would also be a rank 1 tangle, but these here would have rank 2, and so on and so forth. Yeah? And so the definition of rank would just be if you can separate it by not counting the lower ranks, you would just separate this tangle from every other tangle of at least rank 2. Yeah? And this you can do by this separation. Okay, and so we take such a system of separations, making the site containing B as small as possible always, and then you take a minimum order separation. And what we get is something that looks almost like a tree labeling, except it's a DAG. So let's draw it here. Yeah? So what we get from this example would be we can take D as a node and then have an edge, and here we have the separation that was distinguish D from everyone from the others. And here we have B and C. And E, just to redraw the example. And if you just look at the edges separating, then it would look like this essentially, because we have a DAG that's distinguishing the tangles. And so these would be the separations here. So this thing here would be labeled by a separation that contains all of these, all of these, all of these, and this is supposed to be the rest of T. Yeah, so there's more to come. That's of course not particularly nice because I mean, getting a structure that has separations that would not distinguish tangles properly, of course, is not very hard to get. Yeah? I mean, if you don't require these things to be a tree, then this is not so hard. So we need to somehow make it into a tree. And here exactly the observation I just mentioned 2 slides ago will help, because what you can prove is if this happens, that you have 2 tangles like B and C, which of rank 2, and they contain, both of them contain another tangle D on their big side, then this can only happen if what we call they're oriented the same way. So they're sending cross edges, both sending cross edges out or both receiving, but it can't be that you go out here and come in here. And so you will always have this picture. And now in the special case where we know any pair of tangles is L distinguishable, but not L minus 1 distinguishable, we can uncross. Yes, we will see that this actually here is a separation of order L, and this is as well. And then this will give us the tree that we want. Yeah, we would have E somewhere here. And then we would have this separation, let's call it X. Yeah. And then maybe here we have the tangle C. Yeah, and then we can just take this separation here, which is B. And then eventually D. And here we get E. Okay. And this would be the tree you get out of this. Yeah, and that is essentially just a property that you can, in this case, always uncross towards the small side and then this bigger side. Yeah, so no matter if this is 2 or any number of tangles, you would always find a common separation that would kill all of these tangles of rank 2 from all the higher ranked tangles. Yeah. And this is essentially the trick how to get the tree. Okay, and if you do this, then you get this tree labeling here. That's just the properties that we want. And it's not very hard to verify then that you have these special conditions here that every edge actually separates every tangle on its left side from every tangle on the right side. Okay, so why does it not work for the general case, yeah, where we now have a set T of tangles that are pairwise distinguishable, but not always of the same order? Yeah. And here's an example for it. So we have 4 tangles. Let's say these are big cliques or grids, so that they define a tangle, and we can separate them. Yeah, and so if you want to separate, let's say T2 from these 2, then you can take this separation here. Yeah? So you would take these 4 vertices because they go in here, and if you plus this one, and if you separate T3, then you would take these things. Yeah. But T1 can be separated by only this one vertex. Yeah, so because it's the only vertex that sends edges towards T1. Yeah, so here you have order 1 separation separating T1, and these are pairwise only distinguishable by higher order separation. And if you want to turn this into a tree, then we don't actually know what to do, yeah, because it has to be a tree. And so we have T1 somewhere, and because T1 can be separated from everyone by an order 1 separation, we should have an edge that's labeled here by this vertex G. Yeah? But then we also have T3 and T2, so we need an edge that separates, corresponds to these separations here really. Somewhere they have to be present, yeah, because this, if you just uncross this way, it would be too costly. It's 8 vertices. And so there are not too many ways you can do it. And if you look at this tree or any other possible combination, you would always have the property that this separation actually splits off these 2 from T2 and T4. And this edge here would split off these 2. And there's nothing really, it seems impossible to avoid this property. And so what we see here is we have to give up one of the 2 conditions. So either we would allow this edge to be bigger, have a higher order separation, so it's not optimal, then you could uncross, or we have to live with this property here. Yeah. And so we have to live with it. The only nice thing is, and then that's all I want to say about it, because I'm also running late, I noticed. is what's not possible is that you have this situation here, that this tangle would sort of, the separation would perhaps go like this. Yeah? So that won't happen. Yeah, so this will always be this one and this one. If they share a tangle on this side, then they share all of these tangles. Yeah? So it's, yeah, not sure if that makes too much sense, but it's not completely random how we split. Yeah, so it's still a decent tree labeling. Yeah, and yeah, let me not say more about this proof. I think that's good enough.
By the way, as per time, we have about 5 more minutes.
So yeah, exactly. So it's probably better not to say more about this. All right, but still, what you can actually, let me take one more minute. So we want to prove now the general case. We have the set T, and what we just do is we look at the maximum number K, so that there are tangles T and T prime in the set, which are only K distinguishable, but not K minus 1 distinguishable. And this is the first case we proved, yeah, where we have everyone is of the same order. So you get a nice tree labeling for these. Yeah. Okay, and then maybe you have some sets. Yeah, so you partition T, of course, into sets, yeah, which are pairwise K distinguishable, but not less. For each of these, you get a tree labeling, and then we go to K minus 1. Yeah, and we look at the restrictions of the tangles to just order K minus 1 separations, and we get another bigger tree labeling. And then we just have to replace sort of the nodes in this tree labeling here by the inductive, the computed tree labeling things. Yeah. And then you have to show that this all works well. And then eventually you get this different, this theorem here that every set of pairwise distinguishable tangles has a tree labeling. And in the last minute or so, let me say a word for directed tree decompositions, which I'm not going to define. Yeah. So if you now want to translate the setting of tree labelings into proper directed tree decompositions, which are just tree decompositions for the directed graph that properly decompose the vertex set, then you run into exactly the same problems again, that you have overlapping separations and so on. And you have to work quite a bit to get this sorted out. And then you have to allow bigger guards on the edges. Yeah? So we get an approximate version only where the guards along the edge of a directed tree decomposition have quadratic size, essentially. This I don't know if it's optimal. Probably you can reduce it, but I don't know how exactly, and also don't care too much at the moment to get this much smaller. Yeah. Again, I don't actually think you can get an exact number so that it's just optimal with. Yeah. Okay, and that. So let me conclude then. So the directed tangles that we just saw, they formalize the concept of highly connected regions, and we get the tangle tree decomposition theorem that we wanted. With a small blow up, if you go to directed tree decompositions, we have some applications for this. One is to disjoint path problems, so a half integral version, where it's nice, yeah, that you have the decomposition into sort of highly connected pieces in which you can work separately. And we also have, we believe, conjecture, let's say, the result that you have for undirected tangles, that if you can explain the structure of a graph relative to each high order tangle, then you can lift this to a structure of the entire graph. Yeah. This is recent and needs some polishing and so on, and proof checking, but it seems to work. Let's be a bit careful. Which was the result we actually wanted when we set out. Yeah. And so what's left then to do would just be to describe the structure of a digraph relative to a high order tangle when it doesn't have large minors. And that's, of course, open for that looks. Well, that's all for me. Thanks very much. And
Thank you.
Welcome to take questions if there are any.
Yeah, I'll let people just either type it in chat and I can say out loud, or just go ahead and ask. Yeah, we haven't figured out a good way of doing applause on online seminars, but there's a lot of yeah, clapping images.
Those, so I assume that this notion of tree decomposition and Tangle sort of work nicely together, and like you've sort of got a hint of it here. But so I assume your grids give you high tangles, and your tangles give you big grids.
Yeah. So if you have what is the exact? So it's easier to see with Brumble. So if you have a directed Brumble, then of order T, it gives you a tangle of order T over 3, and every tangle gives you a Brumble of order T. So numbers are slightly different from the undirected case, but it's a linear correspondence between the two.
And then you have a relationship between, I guess, the brambles and the grids.
Yeah, between Brumbles and tangles. This is by a factor of what is a third or so in one way, and K is the other direction. For grids, of course not. Yeah, I mean there is this correspondence to grids. Yeah, grids.
For every bramble, there is a grid.
Yes.
That's associated with the bramble.
Yeah. Yes. But this is not linear, and it's not polynomial, and it's a function f.
Another question is that if you've got directed graphs, so if I look at the acyclic directed graphs, or if I think of the strongly connected components, they have a nice structure, and the acyclic components the strongly connected components in a directed graph naturally sit in a directed acyclic graph. They don't naturally sit in a tree. So why are we looking for trees to describe what's going on for the more highly connected things?
Well, because it's a stripped down version of the DAG. I mean, you're right. You would get if you look at directed tree decomposition or a DAG of components, then they would in a way form a tree plus edges going across. And then you would have cross edges in these directions. And so what we want to look at is there seems to be a difference between, well, things that send out edges just in one direction and having a proper cycle, let's say, of tangles. I mean, a cycle of tangles doesn't make any sense, yeah, because you still want to separate. Maybe that would have been the better answer. Yeah, so you can't have clearly, if you look at separation between tangles, then it can't be cyclic, right? Because otherwise it won't be separation. But because you have all these cross edges here, it will turn into a DAG. Yeah, but these we want to factor out, so to speak.
Yeah, I was wondering also if you can state the theorems in some way where like you're building a graph from certain operations from like the basic sets. Like instead of doing clique sums, is there something else you can do, or does this also give a problem for trying to word things that way?
Yes, it does. And the reason being that, well, optimal, if you want to decompose, if you look at guards, minimum order guards for strongly connected subgraph, let's say, then they're not at all nicely behaved like in the undirected case. So if this is your graph and this is, let's say, a strongly connected piece you want to split off, then the optimal guards could sit somewhere here, right? So they could sit completely, and then if you split further into this and go to this piece, and suddenly your optimal guards would sit on this side. Yeah? And so it's not easy. I don't think there's any interesting way of sort of putting this graph together to build up the entire graph tree. This is asymmetry, and this is also something very annoying but unavoidable, and we have proofs for this. You can't reduce it.
All right. Well, thank you again for the great talk. We'll go ahead and stop the recording.